All right, physicists, welcome to our February 10th edition of Physics. Today we are going to be looking at a few common examples of everyday forces and trying to cram them within the context of Newton's paradigm. So remember, in Newton's way of talking about things, we need to explain accelerations. And if we don't have any net forces, we won't have accelerations. So if an object is changing speed or changing direction or both, then we have to introduce a force that will allow us to explain it. So for instance, we have here an example that we did last time where we had one astronaut pushing a space rock one way, another pushing it a different way, and a third astronaut pushing it a different way still. And the way that you find out what the acceleration on that rock is, well, you have to add up your F1 plus your F2 plus your F3 as vectors. So that means you're adding up the x components and you're adding up the y components. And then that is equal to your net force. And then the net force is related to the acceleration through the mass of the object. And the mass of the object is this object. It doesn't have anything to do with the masses of the astronauts. And last time we also introduced a new unit called the Newton. This is a 1 kilogram. It's a little bit, it's about 2.2 pounds. It feels pretty hefty. And the idea with one Newton, the Newton being our new unit of force, which in base units is a kilogram meter per second squared. What it means is that if I take this, I put it on a frictionless surface. So think like a hockey puck, a kilogram weight hockey puck that's on a very slippery ice rink or something like that. And you push it with 1 Newton for 1 second, what happens is that at the end of that 1 second, the puck continues to go at 1 meter per second. Okay, and remember with Newton's first law, if it's just moving, you don't have to explain that. That's the natural way of things in our Newtonian way of thinking, is that if things are just moving, that's fine. That's how things like to be. If they're staying still, that's also fine. The thing that you need to explain is if their speed or their direction changes. So if they're accelerated. Okay, here's a quick concept check. Remember, everything I'm going to talk about has to do F equals ma. That's Newton's second law. The graph shows the velocities of two objects as a function of time during the intervals a, b, and c indicated. Net forces Fa, Fb, and Fc act on the objects respectively. If the objects have equal mass, which one of the choices is the correct relationship between the magnitudes of the three net forces? Okay. Now notice at the very beginning of the story, this is a velocity versus time graph. So in this story, at the beginning, our first object is going forward somewhat quickly. It's getting faster here. It continues to get faster, but at a slower rate, and then it levels out at some constant speed. Our second object is standing still at the beginning, and then it begins moving forward, getting faster and faster and faster and faster and faster. And then it continues to move forward, but it's getting slower as it moves forward. Okay, so that's the story that, remember, positive velocity means you're moving forward, even if the velocity is getting smaller. So it asks us the magnitude of the three net forces. Well, as Newton's second law says, the F net is related to the acceleration. So here we're just talking about in one direction. The biggest slope will tell me which one has the biggest acceleration. Biggest acceleration means biggest force. So in this case, FC is the biggest. FA is next. And then FB. Okay? And I think I have those backwards, but FC is bigger than FA, which is bigger than FB. Okay. So that's the basic idea. We have objects which are being accelerated, and the biggest acceleration will tell you which one has the biggest force on it. Okay, and last time, this is just another one of your homework problems that I hope you tried, and so I'll go over it quickly just to make sure that everyone is on the same page. If only 2 horizontal forces act on a 3 kilogram body, okay, so there's the mass. One of them is a force of 9 newtons going east. Never eat shredded wheat. 9 newtons. Let's call that F1. So if we have F1, it would be 9 newtons, comma 0 newtons. All of the forces in the x direction, none of it is in the y direction. And the other is 8 newtons acting at 62 degrees north of west. So there's your angle. Let me just write in 62 degrees there. And this is pointing in the minus x direction, so your F2 would equal minus 8 newtons times cosine of 62, comma, and then for the y component, it would be 8 newtons times sine of 62. Okay, so there's your x and your y components. If you want to find your F net, it's going to have an x component, which is 9 newtons, minus this number. And then your y component is going to be 0 newtons plus 8 newtons times sine of 62. Okay, so that gives you your net force by adding your x components and your y components together. And then if you want to find your acceleration, it's going to be that F net divided by the mass. So you're going to have to take each one of those components and divide it by 3 kilograms. So then that's going to give you a vector. That's the acceleration, and that's going to be in terms of meters over seconds squared. And then if you want to find the magnitude of that acceleration, you have to use your Pythagorean theorem. So use the x component squared plus the y component squared and take the square root of that. Okay, so that was one of your homework problems. I hope people tried that and didn't find it too terrible. So today we're going to talk about a couple of trickier examples. The ideas are pretty simple though. Let's say that we have an object like this. The gravitational force is that heaviness that you feel of the Earth's gravitational field pulling it down, okay? And what we're going to see in another slide or two is that the amount of force is going to be the mass of the object times g. That's that 9.8 meters per second squared, which it turns out is the same units as if you said newtons over kilograms. So that's the idea. Next is going to be the normal force. So if I go ahead and put this down on a surface, like a notebook, now gravity is pulling down on the object, and this surface is pushing up on it. So those two are going to cancel out. Now that gets trickier, as you'll see at the end of today, if I slide this down, because what continues to happen is that in the perpendicular direction, gravity continues to be counteracted by the surface, but at the slope, gravity is not acting just in the direction perpendicular to the surface. Now, if I pull my object along a surface, after I get it going and it's going at a constant speed, I have to explain that constant speed as being the product of no net force. So in that case, if it's just sliding along at a constant speed, then the force of my pull is counteracted by the force of friction. So that's a little bit of a tricky thing to think about. We will talk about this extensively, probably starting on Friday and into next week. And then the other last thing that is going to take us some thinking is the idea of a tension force. And so here's my block. I'm holding it on a string. This string is pulling up on the mass, and it's pulling down on my hand. Okay, it's pulling up and it's pulling down. So the tricky thing about these tension forces is that they act on different objects in different directions. So we're going to do a couple examples with that too. Okay, so first let's think about the gravitational force. The amount of stuff, so we want to first distinguish between the mass of this object and its weight. And the mass is the amount of stuff, so that's what you measure in kilograms. 1 kilogram is the amount of stuff that's here. It makes it hard for me to accelerate this thing. And if I'm on Earth, I experience a gravitational pull, okay? And the way to think about this is, as we'll talk a lot more about later, around the Earth there's kind of, think about this object called the gravitational field that has a direction every point around the Earth. And this gravitational field you can just think about as hanging out in space. And at every point it has a magnitude and a direction. As you get farther away from the Earth, it gets a bit smaller. Okay, so the moon is experiencing less gravitational force from the Earth than it would if it were sitting on top of the Earth. And the amount of force that you get is multiplying this g, which is 9.8. It's about 9.8 newtons per kilogram. Keep in mind this unit is also the same as meters per second squared. Now, you might say to yourself, well, why have we just been able to use that 9.8 so glibly as the acceleration of an object? Well, take a look how this works. F equals, in free fall, we have F equals ma. Okay, the force on an object is mass times acceleration. In free fall, the only force acting on a body is gravitational force. So I put mg equals ma, so ma, and there I get my result. I divide both sides by m. The size of the acceleration on that object is the same size as the gravitational field strength. Okay, so you might think that I'm pulling a little bit of a trick there. Maybe I am. But the idea is that the cause of that gravitational acceleration is the gravitational force, and F equals ma in this Newtonian paradigm, so it turns out that the gravitational field strength is the same as the gravitational acceleration, regardless of mass. The mass cancels out on both sides. Okay, now, just as a quick concept check, this is 1 kilogram. So if I hang this up on a scale, what force should I see? And I'll do it right here. If you said 1 Newton, the force is actually around 9.8 newtons, okay? So right around 10 newtons for 1 kilogram, okay? And that's because the gravitational field is pulling on it. Okay, as I said, the normal force is the force that a surface pushes back on an object that's in a gravitational field. So this surface is pushing back up on this mass, and that's why the mass doesn't fall down. So in normal cases, when you just have a flat surface, this normal force has the same magnitude as the gravitational force. They're just in opposite directions. F normal is up, gravitational force is down. And just to be clear, normal doesn't mean it's like average or something like that. Normal is just math talk for perpendicular. So it's just saying that force is always pointing perpendicular to the surface regardless of what direction the surface is oriented at. So here's a, I'm going to pause, sorry. Okay, we're gonna, sorry, I'm replacing this with a slightly simpler problem that I think is a little easier to understand. Okay, so here's a problem that's similar to one that I gave you on a fireman sliding down a pole. And so here we go. We've got an 80-kilogram person is parachuting and experiencing a downward acceleration of 2.5 meters per second. So this happens when people jump out of an airplane, you pull the parachute, you continue to go to accelerate downward for a while, but you're slowing your rate of acceleration. So instead of 9.8 meters per second squared, you're only accelerating at 2.5 meters per second squared. And, whoops. And what we want to find out is what does that imply about the upward force of the parachute on the person? Well, in this case, F net is going to be the sum of the parachute and then pulling down would be the force of gravity. And so that's your F net, and you would say that equals the mass of the person times A. Okay, and often I will draw a little drawing like this where I represent the person not as their full expression as a vibrant soul, but instead as just a dot with a mass and a couple of arrows indicating the major forces on there. So there's the force of the drag from the parachute. And then there's a bigger force going down, which is the force of gravity. And so when I write this, I should keep in mind that the acceleration is going to be downward. So if I put my F parachute minus mg, so that's going to be 80 kilograms times 9.8 newtons per kilogram, that equals 80 kilograms times a minus 2.5 meters per second squared. Why did I put a minus? Because it's a downward acceleration. It's the same direction as this, okay? So let's do a little bit of algebra, and you find that the parachute equals 80 kilograms times 9.8 newtons per kilogram minus 80 kilograms times 2.5 meters per second squared is the same as newtons per kilogram. You can check it out because newtons is kilograms meters over second squared. Okay, so this force of the parachute is going to be smaller than the magnitude of the force of gravity, but definitely not 0. Okay, now, when we have tension forces, as I said earlier, that's a little tricky because this tension force in this string is pulling down on my hand, but it's pulling up on this mass right here. So the direction that a rope pulls on an object depends on what part of the rope you're at, right? So I think the easiest way to see this is with a classic problem. Okay, just to sort of hammer this point home again. That's a failure. Okay, I'm gonna put, let me, I should have workshopped this a little bit more before the video. Okay, so I'm gonna hang this, and I have one scale here and another scale here, and just to give you sort of a clear demonstration of this, remember the force of gravity on 1 kilogram is right around 10 newtons. And so the tension pulling up, this one reads 10 newtons pulling that way, and then this scale reads 10 newtons pulling that way. Okay, so that's the idea that we have here with these tension forces. And here's a classic problem where I have 2 blocks. One of them is, in this problem, a 3 kilogram block, and the other one is a 2 kilogram block. And they both are being pulled on by the tension force of this rope. The 2 kilogram block is being pulled upward by that tension, though, and the second rope is being pulled right by that tension. Okay? Now, the net force is going to still be pulling them downward because this block H has a force of gravity pulling it down. It has a tension force pulling up. The force of gravity is going to be bigger than the tension force, so this is going to accelerate. My other block is also going to accelerate, and because this rope is taut between the two, the magnitude of the acceleration of the 2 blocks is going to be the same. The direction is going to be different, however, because this block has a force of gravity pulling down and a normal force that are canceling each other out. So all of the force on this block S is going to be, the net force is going to be in the x direction, and the net force on our block H is going to be in the y direction. Okay, this is called an Atwood machine. This is one of the classic types of physics problems. Okay, so here's our block S. It's free to move along its horizontal frictionless surface, and the net force, if we draw our free body diagram, it's going to be F normal, F gravity, those cancel out, and then what's left over here is the tension force pulling it this way. And let's use a capital M for that mass. And then our second block, our little m, that's our 2 kilogram block, has a tension force pulling up. And the key to this problem is that this tension is the same magnitude as that tension, but they're in different directions. And then it has a force of gravity pulling down. So the force of gravity in this one is big M times the gravitational field strength. The force of gravity in this one is little m times the gravitational field strength. So let's write down a equation. We're going to translate each one of these free body diagrams into an equation. So for this one, we're going to write an equation in the x direction. So the force, the tension, okay, equals m times a. Sorry, let me use a capital M times A. Okay? And then for our second object, I have tension going up, and I have little m times G going down, and that equals, so what we're doing in both of these cases, it's F net equals m times A. T minus mg equals little m times A. Okay, now our question is asking us to find the acceleration of the block as the acceleration of the block h and the tension in the chord. Well, here's my route. Let's find the acceleration. I can do that because I can substitute this in for the tension right there. So ma minus mg equals ma. Okay. So if I want to go ahead, I can then say that I'm going to move this mg over. I'm going to move this m over to the other side. So ma minus little m a equals mg. Whoops. I made a mistake here. Okay. Let me try to explain why this is a little mistake. This tension is in the same direction as the acceleration. T minus mg, this gives me my force pulling up. This gives me an acceleration that I can see from this is going to be down. So let's put in a minus sign there so we don't get confused. Okay? We'll put in a minus sign. And I'm going to put that minus sign here. Okay, so this is the same equation. All I've done is I've put in capital MA for the mg. And then so I'm going to have MA plus little ma equals mg. I'm going to factor out the m plus little m times a equals little m times g. And I get my a equals little mg over m, big M plus little m. Okay, so that there's a couple little tricky steps from this step where I made sure that I put in the minus sign on my acceleration explicitly to the point where I went ahead and compared the forces in the x direction and the forces in the y direction. So there's a couple little hitches here. But notice what it's saying overall. It's saying essentially that this acceleration is little m over big M plus little m. So that's going to be 2 over 2 plus 3 times g. The acceleration is going to be 2/5 of the gravitational acceleration. If you want, you can go ahead and find out what the tension is, because you can take big M times that number to find the tension in newtons. But the thing I want to stress here is that this acceleration is smaller than the acceleration that you would just get in free fall. Now that makes sense, because if you just had this block falling freely, there would be no force pulling back on it. That's not the case here. The tension force is pulling back on the block, so it doesn't fall. Its speed doesn't increase as quickly as it would if it were just under free fall. Okay, so that's the sort of story that we're telling here. You set up the F equals ma for each object and try to do it consistently. So the Atwood machine is a little bit of a tricky example. Let's do one that's a little easier. In this case, we have a a bunch of masses that are each connected by strings, and for some reason, maybe we're doing this type of thing where we have a scale in between each one. We know what the tension is in each one of these strings. So we have A, B, C, and D. And we're given the longer top chord over a frictionless pulley pulls with a force of 98 newtons. So that's 98 newtons right there. And then you have a tension in each one of these of 58.8 newtons. And we'll call that T1. And then you have T2, a tension on that one of 49.0 newtons. And then T3, which is 9.8 newtons. Okay? Now, what I want to stress is that in each one of these cases, we can draw a, let's just call that T naught, why not? You can draw a free body diagram for each one. So for instance, for A, we would have mass of A, don't know what that is, but we do know the tension pulling up, T naught, that's the 98 newtons, and we know what's pulling down, which is 58, or T1. However, you notice that T naught and T1, this is a bigger force than that. What gives? Well, it turns out that there's another force that's also pulling down on this, which is the force of gravity. So this is Fg. And if I want now, I can set up this equation because I have a free body diagram, I have forces pulling up, forces pulling down, and I can do F equals ma, but in this case, the mass is, the acceleration is 0. Okay, so let's do an F equals ma. I'm going to have T naught minus the force of gravity, which is going to be ma times g, minus T1 equals 0. Okay. So I can set up this as 98 newtons minus ma times 9.8 newtons per kilogram minus 58.8 newtons equals 0. Okay? And from that point on, it's just algebra. And so for each one of these figures, so for instance for FC, you're going to have T2 pulling up, T3 pulling down, and some force of gravity from C. And so in that case, your equation would be T2 minus mcg minus T3 equals 0. Okay, and so in each case, you're going to go ahead and find out what the mass of the disk is. And it shouldn't be too bad. The key thing to realize, though, is that all you're doing is you're adding up all of the forces, and because you don't have any acceleration, the sum of all those forces equals 0. All right, now, in this chapter, we're not dealing very much with frictional forces. The reason we're not dealing very much with frictional forces is that there's a little bit of subtlety in having to deal with it. For instance, let's say that I pull my mass along slowly, but it's moving at a constant rate. In that case, the force that I'm applying in this direction and the frictional force in the opposite direction have to be matched, because if I'm not accelerating in the Newtonian picture of things, I don't have a force on me. On the other hand, I could pull this more quickly and still not have it accelerate. In that case, I might be applying a bigger force, but then in that case, my frictional force is also bigger. So somehow we have to deal with the possibility of there being different sizes of friction for the same object, and so this all gets a little muddled, and we're going to have to think through it a little bit more carefully. And your book does that in chapter 6. So this week we're just doing chapter 5 stuff. But that's okay. Even without friction, there is a type of problem that is genuinely tricky. And let's look at this type of problem. This is a problem that's done extensively as a example in your book, where you have a force of tension pulling up, and in this case, they're asking, if you have that amount of force pulling up, what's the acceleration of the object? Now, the reason why it's tricky is that instead of simply having the normal force and the gravitational force counteract each other, in this case, the gravitational force, that's your mg, can be split into two directions, okay? And this part of the force and that part of the force, they're perpendicular, so you can do that. It's legal. It's the rules of the game for vectors, is you can always split it into two perpendicular parts and express a vector as the sum of two perpendicular vectors. But look what happens. This normal force is only counteracting the part of gravity that's in that y direction. The force of gravity that's in the x direction, is now counteracting the tension force that's acting parallel to the surface. So in this type of a problem, if you want to set up your F equals ma type of equations, in the y direction, you're still okay. But what we've done now, we've set up a coordinate system where our y and our x are tilted to go along with the surface. Now, we can do this. Why can we do it? Well, all right, think about it in terms of this. If you have this angle and that, and you say, okay, your gamma, because this is 180 degrees, is going to be 90 minus theta. Then if this is also a right triangle, then this angle has to be theta again, and this angle has to be gamma. So if I want, I can always draw it like this, where I have I'm at an angle. Okay, let me draw it not so obviously, but there's my theta. And now I'm going to split up my force vector from gravity into a part that is perpendicular to the surface and a part that is parallel to the surface. So this one is going to be, this is my theta, this is going to be mg, this is opposite that angle, so mg times sine of theta, and this one's going to be mg times cosine of theta. And so if I want to set up my F equals ma type of equation for the horizontal direction, so now I have a normal force pushing up, I have a tension force of a rope that we're saying is pulling on it. So my F equals ma type of equation in the x direction would be T pulling in the plus x direction minus mg sine theta equals mass times acceleration. Okay, so that's a little tricky, especially if you really have it stuck in your head that cosines go with x directions. In this case, if you look at the right triangles, the x direction is going with the sine of theta. Okay, so it's a little tricky to think about. I gave you one homework problem like this, and I encourage you to think it through. This is just like what I said on the last one. The way to remember it is to draw this triangle like this, where this is theta, this is also theta, gamma, gamma. Okay? In figure 5.536, let the mass of the block be 8.5 kilograms, and the angle be 30 degrees. Find the tension in the cord and the normal force acting on the block. Okay, so it's as before. You have F normal, Fg, the force of gravity, and then your tension force right there. And when you don't have any motion, those are all canceling out. So to find the tension force, you would just add up, there's your theta, same as this theta. You would have your F normal. Oh, we're trying to find the tension force first. Oops. So the tension force minus this component of the gravitational force, so minus mg times sine of theta equals 0. Why does it equal 0? Because it's not accelerating right now. So this is F equals ma. A is 0, so this is 0. For part B, you would have the normal force pushing up. Remember, we're saying this is the x direction, this is the y direction, minus mg cosine theta. Okay, that's this part. So this minus that, again, equals 0. Then it says, in part C, if the cord is cut, find the magnitude of the resulting acceleration of the block. Well, if that cord is cut, the normal force and the component of the gravity of the gravitational force that's acting in that direction, those are still going to be balanced. It's not going to suddenly fall through the surface. What's going to happen is that this tension goes to 0. And so for part C, what you're essentially doing is you're using this same equation, minus mg sine theta. So this is your F equals ma. But you're not going to put in 0 for the acceleration anymore. You're going to have this be m times a. F equals ma. We took away one of the balancing forces, so this force, the force of gravity, just in this direction is what's causing the acceleration. So that's why you get that mass times acceleration. Okay? So this will be a negative number in this setup for the equation. If you're looking for just the magnitude, you can take the absolute value of that, and it should be a value in meters per second squared. So that object is going to be getting faster and faster, and we don't care about friction. Okay, so that's one type of tricky one. Let's look at the only other example I gave you in this homework set, the homework set that's due next Monday. And in this one, you have a real-life character, John Masses of Belgium, who did weird feats of strength. And here's a picture of him trying to move these passenger cars by pulling them with his teeth. Okay. I had to Google it to see whether it was real. It turns out Yeah, real guy. Now, essentially, we're going to do the same thing. F equals ma. The two cars together weighed 700 kilonewtons. So they have some force of gravity on them. And these cars, okay, so he moved railroad cars. He did so by clamping his teeth down on a bit that was attached to the cars with a rope and then leaning backwards while pressing his teeth against the railroad ties. The cars together weighed 700 kilonewtons. So M times M of the cars times G equals 700,000 newtons. Okay, so if you want to find out what the mass of the cars is, you can go ahead and divide it by G, by that 9.8 newtons per kilogram. Assume that he pulled with a constant force that was 2.5 times his body weight at an upward angle of 30 degrees from the horizontal. So there's the force of John Masses. And it's at some angle of 30 degrees. Okay. So, they're being a little tricky about this. They say that the force that he's applying is 2.5 times his body weight. Okay. So, the force that he's applying is going to be massive John Masses, which they give you as 80 kilograms, times G times 2.5. It says, neglecting any retarding force from the wheel rotation, find the speed of the cars at the end of the pull. Okay, so he does this he pulls them for 1 meter. Now the idea is this. There's going to be some normal force here. The force that he's pulling up is merely going to, it's going to lessen the normal force because he's providing some of that upward pull. The only force that he applies is going to be the one that's in this direction. Okay? So if we're looking at the cars, what we're going to have to say is the mass of the cars times acceleration in this x direction is going to equal this force that he's applying, and we just want to take the x component of it. So that's going to be cosine of 30 degrees. So that's going to allow us to find what the acceleration of the car is in that x direction. Once we know that, we can use our equations for accelerated motion. So a good one might be this one. So if he's moving the cars by 1 meter, let's say that they're starting out at a position of 0. This would be 1.0 meter. Then you could use this acceleration. And we assume that the car started out not moving, so its initial velocity is 0. And you want to find that final speed, so there you go. You're going to use it, this equation. You're going to find a final v given the a. All right, so there's a lot going on in a problem like that because I'm asking you to find the acceleration, use your constant velocity motion or constantly accelerated motion models to find a speed at the end of the story. So kind of a lot going on, but I think that what I've just said should help you get through it. Okay, so on Friday, it is a Friday, so we will have an online Canvas quiz. So keep that in mind. Those open up Thursday at midnight, so you can take them anytime on Friday. On Friday, please bring some questions because this homework set is due this coming Monday. So if you have any questions about this, I want them to get answered in class on Friday. Okay, so we covered quite a bit in today's video. The gravitational field is giving our mass its weight. and you find that weight by taking mass in kilograms times 9.8 newtons per kilogram, or 9.8 meters per second squared. The normal force is acting perpendicular from the surface, which means that when you have an object just sitting on a surface flat, the normal force has the same size as the force of gravity, but when it's tilted, the normal force is not counteracting all of gravity, as gravity will have some component that's pulling down. And that's what we've been working on in the last two problems, where you have an inclined surface, so you have to worry about components of the force. Okay, so take a shot at your homework, come in with some questions on Friday, and good luck. Thank you for watching.